You use it every single day, probably without even thinking about it. It's the most important piece of software on your computer, your phone, well, pretty much everything. And today we're going to pull back the curtain on this invisible conductor that makes it all possible, the operating system. So let's start with a basic question. A computer is this incredibly complex box of circuits, wires, processors, and memory chips, right? So how is it that you and I can just click on an icon to watch a video or type up a document without having the first clue how a hard drive actually stores a single byte of data? Well, the answer, the hero of our story today, is the operating system, or the OS for short. It's this powerful, silent partner working tirelessly behind the scenes, acting as the master translator between our simple requests and the super complex language of the hardware.
So here's our game plan for figuring this all out. We'll start with why we even need an OS. Then we'll look at its main building blocks. We'll take a quick trip through history, see how they're put together, use Linux as a real-world example, and then we'll wrap it all up. Sound good? Let's dive in.
All right, Section 1, the invisible conductor. Before we get into the what, we really need to understand the why, and it all comes down to solving one massive problem: complexity.
So at its most basic level, an operating system is just this layer of software that sits right in between you and the physical guts of the computer. It's a translator, a manager, and a kind of traffic cop all rolled into one.
I mean, just imagine the chaos of trying to talk directly to your hardware. Every single component, your graphics card, your keyboard, your Wi-Fi chip, they all speak their own weird, complicated language. The OS steps in and creates one simple, unified way to talk to everything. It just hides all that messy complexity from us.
So really, an OS has two main jobs. First, it acts as an extended machine. It presents this clean, simple version of the computer for our apps to use. And second, it's a resource manager, which means it has to fairly and efficiently divvy up all the computer's resources, like who gets to use the processor, who gets memory, and so on.
And that brings up a really important question. What happens when you've got your web browser open, you're playing music, and maybe a game is running, and they all want to use the CPU and memory at the exact same second? How do you stop it from becoming total chaos? Well, that is the core challenge, and it leads us right into our next section.
So, how does the OS juggle all of those competing programs? That brings us to Section 2, the building blocks. Let's pop the hood and see what key parts make this whole thing work.
The absolute heart, the brain, the command center of the entire operating system is the kernel. This is the real boss. It has total control over everything. It decides which program gets to run when, it hands out memory, and it handles all the communication with the hardware. It's so important that it runs in a special, protected mode to make sure nothing can mess with it.
Okay, so if the kernel is the deep down core, how do we talk to it? Well, that's where the shell comes in. The shell is simply the user interface. It could be the graphical one you're used to with all the icons and windows. That's a GUI. Or it could be a text-based command line. Either way, you give a command to the shell, and the shell passes it along to the kernel to get the job done.
Now, when you tell the shell to launch a program, say you double-click an icon, the OS creates what we call a process. A process is more than just the program's code. It's that program in an active state. It's been loaded into memory, and it's actually up and running. This is the basic unit of work that the OS has to manage.
And here's where it gets kind of cool. Processes can actually create other processes. So an initial program might launch a child process to handle a specific task, and that child could launch its own children. This creates this whole family tree of processes that the OS uses to keep track of who's doing what.
So, you've got your program running. It's a process, and it needs the kernel to do something for it, like read a file from the disk. It can't just barge in and command the kernel directly. That would be a security nightmare. Instead, it has to make a formal, secure request called a system call. Think of it like ordering food at a restaurant. You don't go into the kitchen yourself, you give your order to the waiter. System calls are the official menu of services that the kernel offers.
Now, all these amazing ideas, the kernel, processes, system calls, they didn't just appear out of thin air. They evolved over decades of trial and error. So for Section 3, let's take a quick journey through computer history to see how we got here. You can really map the evolution of the OS right onto the evolution of the computers themselves. In the very first generation, there was no OS. You programmed the hardware directly. The second generation gave us batch processing, which is a way to just line up jobs and run them one after another. The third generation was a huge leap. We got multi-programming, the ability to juggle multiple jobs at once. Then, the fourth generation brought us the personal computer and the friendly graphical interfaces we all know and love. And now we're in the fifth generation where computing's just everywhere, on all our mobile devices.
Okay, so just like there are different ways to design a house, there are different ways to build an operating system. So for Section 4, let's look at the different architectures, or the basic blueprints of an OS.
There are really three main approaches. You've got the monolithic kernel. Think of this as one giant single program where everything is interconnected. It's really fast, but if one small part has a bug, it can bring the whole system crashing down. The opposite is the microkernel, which keeps the kernel as tiny as possible and runs everything else as separate programs. This is much more stable, but can be a bit slower. And that's why most modern systems like Windows and Mac OS use a hybrid design, trying to get the best of both worlds, performance and stability.
To make all this theory a little more concrete, let's look at a really famous real-world example in Section 5, the world of Linux.
The whole story of Linux kicks off in 1991 with a university student in Finland named Linus Torvalds. He was studying operating systems and got really frustrated with the limitations of the educational OS he was using. So he just decided to build his own, as you do. And that little project ended up changing the world of computing forever.
Now here's a super important point that trips a lot of people up. Linux itself is not a complete operating system. It's just the kernel, that central core part we've been talking about. To get a full, usable system, you need what's called a distribution, like Ubuntu or Fedora. A distro takes the Linux kernel and bundles it together with a shell, all the other system software and applications to give you the whole package.
And that brings us to our final section, what you know now. If you're starting out in computer science, or even if you're just curious about how your devices work, you now have a fundamental toolkit for understanding them.
So let's do a quick recap. We know the OS has two main jobs, Resource Manager and Extended Machine. We know its key parts are the kernel, the shell, and processes. We know there are different blueprints for building one, like monolithic and microkernel. And we know that Linux is an incredibly powerful kernel that forms the foundation for countless devices. Honestly, you now have the conceptual framework for your first big steps into practical computer science.
So there you have it. You now understand that invisible conductor that orchestrates absolutely everything your computer does. You've seen the logic behind the magic. The only real question left is, now that you know how it works, what kind of music are you going to make it play? What will you build? What will you create? What will you explore next? Thanks for joining me.